Hello everyone. I welcome everyone for the course, the Manipulated Robotics. It's a theory course. So today's topic is how do you represent a robot in Cartesian space? Okay, or where is my robot? Where is my robot? Actually, this is the basic serial manipulator. Let me take one basic serial manipulator. Here is the joint. Here you have your gripper, and then here it has to pick some cloth. So here let me draw some table. Let me draw some table because the robot has to wipe it. Okay, so let me take one table. Okay, so in this here a water is split. A water is split. Okay, so the robot is given some cloth. The robot is given some cloth. Okay, so the robot has to take this cloth and it has to come over here. It has to come over here means it should be like this. Okay, so here's the gripper. Then it has to pipe it. So this is the task. So it has to move from A to B to wipe this. Okay, this is the task given to this. So actually, this is the machine. Actually, this so we have to give some intelligence to the machine to move from here to here. So for that, first I should know where what is this? Where is my robot is? Okay, so here is my reference frame. So here in robotics we follow right hand rule. Right hand rule. You can keep your right hand and you can curl over that. So you can see that this anti-clockwise rotation. So here, so we should know where is my robot. That is at this point or this frame. I can say this is the frame. Okay, frame, end effector frame, end effector frame as per the reference frame. So this is my universal frame. So you should say that I mean the end effector, how it is oriented, how it is positioned, how far it is away from this reference frame in terms of distance, how far it is away from. So this is my end effector frame with respect to here. Let me say U frame. How far is my robot is okay. So that you should know in terms of I mean, translation. I mean, how far it is, or I mean, moved from that. So next one is orientation. How far it is rotated? Because this, since it is a frame, it may have x-axis like this, it may have y-axis like this, it may have z-axis like this. We have to compare. So here you have to compare this x and then this x. So here we have x. So this x and this x, how far it is rotated. And then this y and this y is how far it is rotated. So this z and this z. So if you compare this z and this z, they are 180 degrees apart. And then if you consider this y and this y means, so they are like 120 degrees apart. So you should be able to say where is my robot? Okay, where is this end effector origin, or where is the gripper with respect to the reference frame? And similarly, so that once you know that, you can I mean you can make a plan and you can make the robot to move on this line. So for every point you should know what is the I mean what is the joint parameters theta 1, theta 2, etc., and that too with respect to this. So for that you should know how do how to represent a point in space. So we'll start from there, then we'll move to frame. So slowly we'll discuss about transformation. So in this we are going to discuss about transformations. Okay, what do you mean by transformations in robot? So it is orientation, orientation in XYZ, and translation in XYZ. So this is these two actions represents transformations. So we are going to see what is transformation. So now we understood why do we need transformation, so that we'll be able to make a robot to do a particular job. So for that we should be able to know where is my robot at every point of time. Then only suppose if it goes beyond the, I mean, it goes off the line means we can make the robot to come back to the original trajectory. So for all this, we need to know where is my robot. For that, the answer is transformations. And then there are two transformations. One is orientation and translation. So further, this is the first point. So how do you represent a point in space? So this is the point. How do you represent a point in space? So here this x, y, z. So it always follow right hand coordinate system x, y, z. Okay, so x, y, z is the reference frame. So here, okay, we can put this is the reference frame. This is the point. So how do you represent a point with respect to x-axis, y-axis, and z-axis? So this point, if you draw a line, means so this is AX. Okay, so this point is on this line. Okay, this line. So this distance is AX. Okay, this is AX. Okay, and then this one is so this is on. Okay, then y-axis is this point. Y-axis is this point. That is BY. And then z-axis is CZ. Okay, so how do you represent a point? So it is AX into this vector. Okay, so I can say unit vector. Okay, then in that way I can represent next here by. So by into for y-axis it is j vector plus cz into k vector. Okay, so this is how we can represent a point in the vector format. Okay, ax into I vector, by into j vector, cz into k vector, and the ijk are the unit vectors. Ijk are the unit vectors, and then x, y, z are orthogonal to each other, which is 90 degree to each other. Okay, x, y, z, which is orthogonal to each other. So in this way, we can represent a point in space. So now we'll discuss how do you represent a frame in space. So here, this is my x, this is my y-axis, and then this is my z. Okay, because it follows right hand coordinate system. Okay, so this is my reference frame. This x, y, z is my reference frame or universal frame. Then this is the movable frame. That is NOA. Okay, NO is N is normal, O is orientation, A is the approach one. Okay, so this NOA is the this one is the current frame or moving frame. Current frame or moving frame. Okay, so again let's take this example. Okay, so here so this frame is universal frame, let's say, and then this frame is one frame, and then this frame is end effector frame. Okay, so we have different frame. So in this, U frame is the fixed frame. U frame is the fixed frame, whereas one frame, comma end effector frame are the current frame every time. Because suppose if you are discussing with one means that becomes a current frame, or you are considering only E means that is the current frame. So one comma E are the current or the moving frame. Okay, so that we have to differentiate between that. So that is why X, Y, Z are for reference frame, NOA. This is for moving frame. This is for current frame. Always. So this is the logic we follow. Okay. So now we'll see. So each unit vector. So these are all unit vectors. So this one is unit vector. This one is unit vector. So each unit vector are mutually perpendicular. They are orthogonal to each other, which is 90 degree to each other. Okay. So now we can represent n because this is the frame. Now we are going to represent n with respect to this x, y, z. Okay. So your so already we have discussed, so this n on this is nx. So this is nx, and then with respect to y is ny. So likewise, so nx into I, ny into j, nz into k. So this is how you have to represent a normal vector. How do you represent the orientation vector again? O with respect to x is oxi, oyj, ozk. Okay, so this is the representation of orientation vector with respect to reference frame. Then A is the approach vector, so axi, ayj is the azk. So this is how to represent approach vector with respect to reference frame. So now there are too many elements, so we need a matrix to put it. Okay, so this is always n mean movable frame or moving frame NOA, and then this represents XYZ. So this point says how far, I mean, the current frame x-axis and the reference frame x-axis, both are to be compared. Okay, for example, so this is my x, y, z. Okay, so now I have put like this. So this is my NOA. Okay. So here now I want to compare this and this. Okay. So actually, yeah, first N. So this, in order to fill this, I have to compare N with X. So N and X are perpendicular to each other. Okay. So for that we have to give the cosine. So this NX is called as cos 90. Okay. Similarly, we are going to compare this O with X. O and X are parallel to each other. So it is cos 0. Okay. Then we can compare A with X. So A and X are 90, I mean, orthogonal to each other, cos 90. So in this way, so similarly, next, this one is X with Y. Okay. I mean, N with Y. So this N with, so N and Y are orthogonal. So it is cos 90, and then N and so O and Y. Okay, so they are also orthogonal. So cos 90. And then next one is A and Y are in parallel to each other, so it is cos 0. So likewise, we'll be able to relate the current frame position or orientation with the reference frame orientation. So for that, we need this matrix. So likewise, we should know how to represent a frame in the matrix format. Okay. So next one is how to represent a frame in a fixed reference frame. Okay. So previous, the same thing only. So here this is X, this is Y, then this is Z, and then this is my universal frame. Okay. So we have to completely represent. In the previous case, I have showed you how to represent the orientation N, O, A. Okay. So this we have done. So how do you, so this point represents orientation. So this 3 cross 3 matrix says orientation. Orientation of current frame. So current frame is here, it is represented as O. And then universal frame they have represented as, sorry, current frame is F, universal frame is they have represented as Y. So 3 cross 3 represents orientation of current frame F with respect to O frame. Okay. And then what is this Px, Py, Pz? How far it is moved away, translated in this, okay? So Px is how far it is away from x-axis, and the Py is how far the current frame is moved away in terms of y-axis, then this is z-axis. So this matrix is called as homogeneous transformation matrix. Homogeneous transformation matrix, okay? Homogeneous, it is 4 cross 4. Okay, and then in transformation means it has rotation plus translation. So this is my rotation part, so which is 3 cross 3. So rotation matrix is 3 cross 3, translation is 3 cross 1. Okay, so altogether it gives you the transformation matrix. So likewise, we'll be able to locate, or we'll be able to relate the current frame with the previous frame, or the current frame, suppose if this is your robot is, you'll be able to say, I mean, what is the relationship between these two? How far it is moved away from one frame in terms of orientation as well as translation. So here, this is the position vector. PA, this is the position vector, and this is the rotation matrix. Okay. So this is how we can represent a frame in the fixed reference frame. Okay. Next one is rigid body. Okay. So robot is a rigid body. So here the same thing, a rigid body. Here also we have NOA. So that is represented in terms of this X, Y, and Z. So the same matrix form, okay, but the name is different, the rigid body. So here this represents how your rigid body is oriented with respect to how rigid body is oriented with respect to O frame, okay. Then this PZ. So how rigid body is translated with respect to O5. Okay, so for that, I mean, the rigid body should be represented in this. So hereafter, remember, we have a 4 cross 4 homogeneous transformation matrix. In this 3 cross 3 represents the rotation part or orientation part. 3 cross 1 represents the translation part, other. I mean, how far it is moved. Okay, so this is about rigid body. So next we'll discuss about the transformation. So now we know the transformation. So transformation means a transformation matrix is an operator. It is an operator given by 4 cross 4 matrix. When applied to a position vector, makes a movement in space through. Okay, so either it has a pure translation, okay, and it has a pure rotation about an axis, or it has combined transformations and rotations. For example, if it is pure translation, means there is no, what do you mean by pure translation? So this is my x, y, z, and then this is my n, o, a. Okay. So when you compare x and x, say they are parallel, y and o are parallel, z and a are parallel, which means so this angle is cos 0. Okay, so the other angle cos 90 is 0. Cos 90 is 0. That is why 100. So here, so this one is n o a. This one is x y z. Okay. So next you are comparing n with y. Okay. So if you are comparing n with y, they are 90 degrees to each other. So cos 90 is 0. So you are comparing O with y. So O and y are parallel to each other, 0. So cos 0 is 1. Okay. And next one is we are comparing A with Y. So A and Y are perpendicular to each other. Cos 90 is 0. Next, we are comparing N with Z. So N is here, Z is here. So it is 90 degree to each other. Cos 90 is 0. You're comparing O with Z. So O with Z is they are perpendicular to each other. Cos 90 is 0. Then you're comparing A and Z. So A and Z are parallel. So cos 0 is 1. Okay. So this matrix, identity matrix purely says it is purely, or it is not, there is no rotation. It's purely translation. So how far is the translation? Okay. So this distance. So how far it is, I mean, we should be able to give this point. So that is how far it is away from the reference frame in y-axis, x-axis, z-axis, and in order to make it as a square matrix, we have to put like this. Okay, so this is called as a pure translation. Next one is a pure rotation. Okay, pure rotation means you have some value. So you have some value, but in the translation part, it is 0, 0, 0, 0, 1. Okay, so here it is, so we are going to see that. We are going to see how to represent a transformation matrix about a axis. So here this content says rotation, but it is rotated about either x-axis, y-axis, z-axis. We are going to do that. So this is the matrix for pure rotation, but no translation. Okay. Then you have both. This is, you have both. So here, this represents orientation or rotation about an axis. This represents your position vector. So this is the example for pure translation. This is an example for pure rotation. This is the example for both the combination of rotation and the um, translation. Okay. So next, what are the advantages? Okay. So representing all transformations as matrix multiplication. Like suppose here, this is my frame, this is my frame, this is my frame, this is my frame, and these are all link, okay, binary link. Okay, so here we have end effector. Okay, so let me say this is my end effector frame. So let's start with the 0 frame, 1 frame, 2 frame, and 3 frame. So how do you represent transformation map E with respect to frames? So for that, I have to start from here. E frame with respect to third frame, then third frame with respect to second frame with respect to one frame, first frame with respect to 0 frame. So this you have to multiply. Okay. So in order to get the complete transformation, we need multiplication. So matrix multiplication is common in this. So representing all transformations as matrix multiplication. Then capturing composite transformations conveniently. So composite means it has both rotation and translation. Once again, I'll repeat. So this 3 cross 3. 3 cross 3 is rotation. 3 cross 1 is translation. Then this is 1. Okay. So you can capture composite transformations. Okay. And also composite means like if one axis is rotated about x-axis, another one is rotated about y-axis. So we're going to capture, and then we'll see this in detail in the numericals. Next one is we can change the reference frame. Yes, yes, definitely you can change the reference frame, but you have a formula in there. So you can displace a vector. So this is the vector, so you can displace it and representing a rigid body configuration. So and also it is easier to calculate square matrix. Okay, yeah, just take a transpose. Suppose if you want to find R inverse means just take a transpose. Okay, generally for a matrix you need to take the adjoint and you have to take the determinant. Whereas in the rotation matrix, just check the transpose of it, then that gives the inverse matrix. Okay. So next, how do you represent the translation operator, translation matrix operator? So already I have showed you, this is my pure translation. So this pure translation is there is no orientation. Okay, orientation is nil, zero orientation, but you have a translation that is represented by dx dy. So this is the point. So this is my dx dy dz. Okay, so this is the vector. Okay, so now I'm going to represent, I mean, in terms of this operation. So here, this is my frame. Okay, so this is my frame. I mean, this frame is between. So this frame is between this and this. Okay, so this is the frame. So I can say transformation of P dash with respect to P. So this is so here. See, you can see N and N. There is no change. O and O are parallel. A and A are parallel. So when you relate this P dash frame with the P, then this is your transformation of P dash with respect to P. So this is the frame which shows there is no orientation but translation. Okay. So to this, a point is attached. Okay. So point is attached. So now we are going to say this with respect to the reference frame. So this distance is Px, Py, Pz. Then if you just multiply, then you will get this one. So that's why you can represent the transformations in terms of matrix multiplication. So this is pure translation. So in the previously we have discussed how to represent, uh, I mean, only translation. There is no orientation. Now we are going to discuss about orientation. So in this orientation, first we are going to discuss about rotation about x-axis. For that, I need one reference frame. Okay, so this reference frame is x, y, z. Okay, this is the reference frame. Now I'm going to take the current frame. So the current frame is rotating about x-axis. So here this becomes n. Okay, because with respect to x-axis, then you will have some deviation orientation and then some more deviation of theta. Okay, so this is called as o vector. This is called as e vector. Okay, so now I'm going to take one point P and I'm going to project on it. Okay, so I'm going to project this P on this y-axis. So it becomes Py. I'm going to project P on o-axis and then this line becomes PO. Okay, and then this is theta. Similarly, I'm going to project this P on z-axis. Okay, so this becomes PZ. And I'm going to project P on this one, A. Okay, so this becomes PA. So if this is PA means this is also PA. If this is P naught means this is also P naught. So this is theta. Okay, so a simple geometry we are going to make. And let me okay, yeah. So if this is theta, and then I'm going to draw this line. Okay, so what is this? This line is PA is here. So this is PA sin theta. Okay. Okay, then if this is theta, then this one is here. This also PA sin theta. This point is so this point is PA sin theta. Okay, okay. Then if this is theta, then how about this one? This entire line is P naught cos theta. Okay. Similarly, if this is theta, then this one this line is PA cos theta. Okay, so this one is P naught cos theta, this is PA cos theta. Okay, and then here PA sin theta, this is also PA sin theta. Okay, so once again, let me yeah, PA, this one is this is P naught, here P naught. So this is P naught sin theta. Okay, so now let's do that. So first, let us say that. Okay, so here in x-axis, the projection is Px. Okay. In n axis, the projection is n because both are same. Okay. Now I'm going to derive for py. Okay. So py. So what is py? This is py because the point is projecting over here. Okay. But we have the entire point which is p naught cos theta. So P naught cos theta. In this, I have to subtract this area. What is this area? PA sin theta. So minus PA sin theta. Okay, this is my PY. Then what is PZ? PZ is entire thing. So I have to add this point, and this point. So what is this point? PA cos theta plus P naught sin theta. Okay, that's all. So now we are going to put it as a matrix. So it is PX, PY, PZ is equivalent to so here 1 0 0 and then here 0 0 cos theta minus sin theta cos theta. Okay, so here it will be pn po pa. Okay, so you can check that. So px equal to, if you multiply this, pn only, so this is correct. And then py equal to 0 0, then p naught cos theta, yes, correct. And then minus p naught, this one is pnoa minus, so one second, so p naught cos theta, yeah, yeah, p naught cos theta, yes, then pa sin theta, yes, correct. And then this is 0, then p naught sin theta, yes, p naught sin theta, then pa cos theta, yes, okay. So this is what, so what is this? So this is the rotation matrix about x-axis, how much is the angle theta, okay. So whenever, if you want to say, I mean, how the current frame is rotated about x-axis means, then this is the matrix. So the matrix is 1 0 0 0 0 here, cos theta minus sin theta and cos theta, okay. We are going to follow the same for the y-axis, okay. So what is the logic? First you have to take the x-axis, y-axis. So now I'm going to shift it. So x, y, z, okay. And then it is about y-axis, so you have to concentrate on n o a. Okay, so this is n o. Okay, so this is u. Okay, so since this is o, so you have some angle. So this is my n o. This is my a. Okay, this angle is theta. This angle is theta. Okay. So whatever we have followed before, the same thing we are going to follow. So your P is projecting on this one. So this becomes PZ. This becomes PZ. Your P is projecting on A. Okay, so this line becomes PA and this is theta. Okay, your P is projecting on x-axis. Okay, so this point becomes PX. Okay, and your P is projecting on this n. So this becomes Pn. If this is Pn, this is also Pn. If this is Pa, this is also Pa. Then this is theta. Okay. So now, so we know that. So this point, okay, this point is Pn sin theta. Here also, this point is Pa sin theta. Okay. And what else? Yes, this point is Pn cos theta, and then this entire point, this point is PA cos theta. Okay, so let's do that. So first we'll start from PX. Okay, so what is PX? We have to add this and this. Okay, what is this? PA sin theta, and then we go, yeah, PA sin theta, and then this one is PN cos theta. Sorry, PN, yes, PN cos theta. Okay. Next, we'll take PY. PY is equivalent to PO only. So this one, PY is equal to PO only. Then PZ. What is PZ? This entire thing is PA cos theta. Then minus this one. This one is PN sin theta. Okay. So let's make a matrix. px, py, pz. Okay, so now 0, 1, 0, 0, 0, cos theta, sin theta, minus sin theta, cos theta. So it is Pn, Po, Pa. Okay, so let's check one by one. So Px equal to cos theta, Pn. So Pn cos theta. Then 0, P naught. Then Pa sin theta. So Pa sin theta, that's right. Py equal to 0, P naught, this is also right. And then Pz equal to minus Pn sin theta, yes, minus Pn sin theta, okay, 0, then Pa cos theta, yes, okay. So hereafter, if you want to rotate the current frame with respect to y-axis means, then this is my transformation matrix, or sorry, rotation matrix, okay. Then we follow the same for the z-axis. So again, so here z, this is my z, and then A is located. So z means, so this becomes x, this becomes y. Okay. So let's take this point P. Okay. So you have a rotation. So this is theta. Then you have a rotation. This is theta. So this is my n axis, and then this is my o axis. Okay. Then let's project a point on this. So project point P on this. Okay. So this becomes Px. Project P on n axis. So it makes an angle theta. So this line becomes Pn. Okay. Similarly, project P on y axis. Then this entire point becomes Py. Okay. And project P on o axis. So this becomes PO. So PO, this is also PO, this is PN, this is also PN. Here it is theta, here also theta, okay. And next comes this area, this point. This point is P naught sin theta, okay. And then this point is PN sin theta, okay. And then this point is P naught cos theta, and here this point, okay, because here theta up to this. So this point is Pn cos theta, okay. So let's do this. So what is Px? Where is Px? Yes. In order to find out Px, we have to subtract this. So this entire thing. So Pn cos theta minus P naught sin theta. Okay, what is your Py? Py equal to, you have to add. So P naught cos theta plus Pn sin theta. Okay, then Pz equal to Px. So let's do the matrix. So it is Px, Py, Pz. The matrix is cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Okay, so let's put Pn, Po, and Pa. So let's cross check. So Px equal to Pn cos theta, Px equal to Pn cos theta. Then P naught sin theta, yes, P naught sin theta. Py equal to Pn sin theta, yes. Then P naught cos theta, yes, and then this is 0. Then Pz equal to P. That's all. So this is for rotation of, rotation the current frame about z axis by an angle theta. Okay. So this is how you can derive an expression for pure rotation about x-axis, y-axis, z-axis. Okay. So next, okay, so let's say that. So one more thing. So here this is a beautiful example. Okay, so this example says your matrix multiplication is not commutative. Okay, so let's take this. So here you have x-axis, y-axis, z-axis. So here I'm going to first follow. I'm going to rotate this with respect to x-axis. Okay, so you can, if you rotate this x-axis, it goes on top. So like this. So this is the question. Then okay, so here still it is x-axis only. It is x-axis. This is y-axis, and then this is z-axis. Now we are going to rotate about y-axis. So where is y, y? So you have to rotate like this. So it turned. Okay, this is the final position. Okay, and I'm going to try the another order. Okay, so first initially we have rotated this about x-axis. Now I'm going to rotate this about y-axis. Okay, see, first thing is we have done in this order. Uh, One is Rx, we have done Rx, then Ry. Okay. So now we are going to change the order. First, we have to do Ry, rotation about y-axis. So y-axis means so it is rotated like this. Okay. So it just turned. See, you see the apple. So this just turned. Okay. So still it is y, and then this is x, and then this is z. So now you have to rotate about this. So rotate about this, it is turned like this. Okay. So are they same? No, it is not same. So which shows that matrix multiplication is not commutative. This is the pure representation of that point. Okay. We have to we just recollect if you want to rotate current frame with respect to x-axis about an angle theta means what is the formula? 0, 0, 0, 0. Remember this cos theta minus sin theta, cos theta. Okay, this is the formula. Okay. Then if you want to rotate the current frame with respect to y-axis about an angle theta means 0, 1, 0, 0, 0, cos theta, sin theta minus sin theta, cos theta. For all this, we have seen the proof. Suppose if you want to rotate the the current frame with respect to z-axis about an angle theta means so it is 0, 0, 1, 0, 0, cos theta minus sin theta, cos theta. Okay. Yes. Okay. So now we'll see the properties of the rotation matrix. So what is the property? So for example, rotation of x-axis rotation of current frame with respect to x-axis by an angle theta is 100, cos theta minus sin theta, cos theta. So this is the matrix. So let's see the properties of the rotation matrix. So in this unit vector rows and column, which means each row or column of a rotation matrix is the unit vector. So how do you check the unit vector? How do you check the unity? So you have to take square root of 1 square plus 0 square plus 0 square equal to 1. So if you take this in the column wise, so 0 plus cos square theta plus sin square theta equal to 1. Then if you take this 0 plus sin square theta cos square equal to 1, see, and also you can take in the column wise also, row wise also. So for every, in every way, either row or column, it is a unit vector only. So each and everything is a unit vector. So I can put like this. So this is my n vector, unit vector only. Okay, current frame. This is the reference frame. So each row or column of a rotation matrix is a unique vector. That is the first one. Okay. Then second point is the dot product of any two different rows is 0. So shall we do that? If you take a dot product, so this is 0, 0, 0. Okay. If you take a dot product 0, then if you take a dot product, it is minus cos 0 sin theta plus if you take a dot product, it is s theta cos theta. So it is equal to 0. Okay. Or you can take like this 0, 0, then this is plus, this is minus. So this is called as orthogonality. So orthogonality means the dot product of any two different rows is 0. Okay, this is the second point. And then we have proved before that this is non-commutativity. It is not commutative. You cannot change the order. So very, very important. Do not change the order because it leads to a different situation. So do not change the order of multiplication because rotation matrix, these are rotation matrix. We have to study the properties of rotation matrix. So rotation matrices are not commutative. Okay. Then inverse. So if you want to take the inverse, then you can just take a transpose of it. So let's check that. So for example, this one is 1. So if I take the transpose, so what is the answer? 1, 0, 0, then 0 cos theta minus sin theta, then 0 cos theta cos theta. So this is the transpose. Okay. So let's check that we have to take the inverse of it, then that inverse should be equivalent to inverse. So here, if you take the this one means so it is 1 by determinant is so this is 1, and then if you take, you can take the inverse of it, definitely that will be equivalent to this. So R transpose is equivalent to R inverse. Okay, so I think you have studied in your mathematics, like in order to replace this, we have to remove this row and this column, then multiply this cos square theta minus plus me. So this will be 1. Okay, so we'll do that. Okay, so this is 1. I'm taking the inverse of it. So this is 1. Okay, so if you want to fill this, so leave this. So you will have 0 and 0. Yes. If you want to fill this, so leave this. So it is 0 and 0. Okay. Then if you want to fill this, leave this. So it is 0 and 0. Then if you want to fill this, so leave this. So it is cos theta. So it is 0 only. In order to fill this, you have to cancel this. Okay. So if you cancel this, the cos theta minus here it is cos theta. Okay. If you want to fill this, so just remove this. So sin theta. Then if you want to fill this or remove, hide these, so it will be 0 and 0. If you want to fill this, remove this, so you will have minus sin theta. If you want to fill this, you have to hide this, so it is cos theta. Okay. Can you see both are same? So what is the understanding? Your inverse of the matrix is equal to transpose of the matrix. Then you can change the notation also. So TBA, you can change it to AB. Okay, so this is also possible by taking the transpose. Okay, and one more thing is what is the determinant of rotation matrix? So if you take the determinant, it is 1. Remember this. So your determinant of any rotation matrix is 1. Okay. So from this, what did we understand this? If any matrix follows these properties, then that matrix is called as rotation matrix. So what's the first property? Each row or column is a unit vector. Then it is orthogonal. That's why the dot product is 0. Then it is not commutative. Then your inverse is equivalent to transpose of the matrix. So taking inverse is so simpler here. And the if you want, you can change the order. Okay, you can change the order of the frame by taking the inverse of it. Then your determinant of the rotation matrix is 1. If any matrix that follows these properties, then that is called as rotation matrix. Okay, so we'll do some simple problem. Okay, so for that you should know this matrix. Rotation x theta equal to 1 0 0 0 0 cos theta minus sin theta cos theta. Then rotation y theta equal to 0 1 0 0 0 cos theta minus sin theta cos theta. So here minus this is plus here minus. Okay. Then rotation is the theta equal to 0 0 1 0 0 cos theta minus sin theta is theta cos theta. Okay. So let's take one example, a point 4 6 3 transposes the point vector is attached to a rotating frame. Attached to a rotating frame is attached rotating frame from the frame that is from 90° about the axis of the reference frame. So find the point, find P vector with respect to a reference frame. Okay, so let's do that. So what is the takeaway? So this is the point. Okay, 464, 463, 463. This is the point. Okay, that point is attached to a rotating frame. That frame matrix nature is that frame is rotated about 90° with respect to y-axis. So I have to take this formula. Okay, so what is the formula? Cos 90 0 sin 90 0 1 0 then minus sin 90 0 cos 90. Okay, so what is cos 90? Cos 90 is 0 and then this is 0, sin 90 is 1, then 0 1 0 then minus 1 sin 90 is 1, 0, cos 90 is 0. Okay. That has to be multiplied by 460. So you have to multiply this, so this becomes 3, and then this is 6, and then this is minus 4, and this, okay, minus 4. Okay, so from this, what did you understand is, since this is about y-axis, so this y coordinate will not change, okay, and then the other coordinate will change, okay, so this z will, because 90-degree only, so z will move to x value will move to z, but with a sign change, okay, this is the general understanding about this, okay, so then the similar point, so let's take same point, point 234, okay, so this is rotated about 90-degree about z-axis, okay. So this matrix is 0, 0, 1, 0, 0, then here cos 90 minus sin 90, sin 90, cos 90, okay, so that should be multiplied by 2, 3, 4, okay, so cos 90 is 0, minus sin 90 is 1, 0, sin 90 is 1, cos 90 is 0, 0, 0, 0, 1, then this should be multiplied by 2, 3, 4, okay, so when you multiply, this becomes 0, so minus 3, and 2, and 4. So what is the understanding? Since it's about a z-axis, there is no change in the z-axis. So that parameter will never change, but these will be swapped. Okay, so but with the sign change. So this is how we can do any mat any this one transformation. Okay, so now let's, so similarly you can refer the same 2, 3, 4 about 90-degree above x-axis. Okay, so what is that? X-axis means 1, 0, 0, 0, 0, cos 90 minus sin 90, sin 90, cos 90, then the points are 2, 3, 4. Okay, so 1, 0, 0, 0, cos 90 is 0, sin 90 is 1, and 0, sin 90 is 1, cos 90 is 0. Okay, this should be multiplied by 2, 3, 4. Okay, so let's multiply. So this becomes 2, 0, 0 minus 2, then this, no, this is minus 4, and then this is 3. See, since this is about x-axis, so this won't change, but there is a swap between 3 and 4, but with a minus change. Okay, so one more example, let's do the complex, composite transformation. Okay, so a rotating frame or a point is attached. This point is, let's say, 731. Okay, a point is attached to a frame which undergoes the following transformation. So what is the first thing? Rotation about x-axis 90 degree. Okay, then second one is rotation about y-axis 90 degree. Okay, so find the new coordinate. Find P new. Okay, this is the problem. Okay, so let's do that. So first we have to attach the point 731. Okay, then what is the first rotation? X-axis. So x-axis means 1, 0, 0, 0, 1, 0, 0. Then cos 90 minus sin 90, sin 90, cos 90. Okay, then see, actually first it has to do, then second rotation is y-axis. So 0, 1, 0, 0, 0, cos 90, sin 90, minus sin 90, cos 90. Okay, so what is cos 90? 0, 0, 1. 0, 1, 0, then minus 1, 0. Okay, so let's check. Cos 90, 0, 0, minus 1. Then 0, 1, 0, sin 90 is 1. So then here 1, 0, 0, 0, 0, minus 1. Then 0, sin 90 is 1, cos 90 is 0. Okay. So 731, so simply have to multiply this. So 0, 0, 0, then 0, 0, 1, 0, 0, 0. Okay, then 0, 0, 0, 0, 0, 0, 0, this is minus 1, then this is the next minus 1, 0, 0, then minus 0, 0, 0, then 0, 0, 0. Okay, that should be multiplied by 731 is equivalent to 0, then 3, 0. So 0, 3, and minus 1. So 0, 0, minus 1. So here it is minus 7. See the change. So 3, minus 1. So all are changed because of this. Okay. So in this class, we have studied, we have learned about where is my robot, how to locate the robot using orientation and the translation. So here we have studied how to orient a point or how to represent a point in space, how to represent a frame in space, how to represent translation alone, how to represent rotation alone. We have seen the derivation also, and we have seen the properties also. Okay, so in the next video, we will do some problems. Thanks for watching.